Hi friends, welcome to yet another video. In this video, I will be discussing about orthotropic materials. So first of all, I will address the question in the first place why we need orthotropic materials in engineering. Why can't we just live with isotropic materials? In case if you don't mean what is an isotropic material, isotropic material is one which has same properties in all directions. Most of our conventional metals like steels or copper, brass, most of them aluminium, all of this will fall into the category of isotropic materials. Now, let's start with an example where I can demonstrate the importance or the relevance of bringing in orthotropic materials into engineering design. We will start with a very classical example that mechanical engineers often use, that is of a closed vessel. You call it pressure vessel, so we will take the example of a pressure vessel and talk about the relevance of orthotropic material. So as shown in the figure, here is a pressure vessel with both ends closed so that you will develop two kinds of stresses, the hoop and the meridional, or usually in engineering textbooks they are referred to as axial stresses. If you are wondering what are these stresses, in order to appreciate, I have got some figures here. Sorry for that. I've got some figures here. So first we will talk about the axial stress, which is sigma z. So if you cut a cross section perpendicular to the length of the vessel, then you can see here these are the axial forces which will balance this force, this net pressure acting on the cross section. So this is the axial stress on the pressure vessel. And similarly, if I cut a circumferential section, then I will get circumferential stresses as well, as shown here. I won't get into the very details of these things, but for the time being, for a pressure vessel of this kind, equations for the axial stress and hoop stress are shown here. So P is the internal pressure acting inside the pressure vessel, D is the diameter of the vessel, and T is the wall thickness. To give you a bit more detail, this equation is only valid for thin shells. For thick shells, you have a totally different formula. But the key takeaway from this little discussion on pressure vessels is that the stress acting in the hoop direction is twice that of that which is acting in the axial direction. So, for the sake of explanation, let's assume some numbers. Let's say in this case, axial stress is 50 MPa and hoop stress acting on the pressure vessel is 100 MPa. It is twice as that of the axial stress. The designer comes with two design options. One is he is using an isotropic material with a strength of 100 MPa in both directions. For the time being, assume that we are looking at a design with factor of safety equal to 1. Then in the case 2 or in option 2, the designer comes with an orthotropic material with a hoop stress of 100 MPa and an axial strength of 50 MPa. Which one looks more convenient or which one looks more innovative? Obviously the second one. So this little example shows you actually we have to select materials for a particular structure after looking at the kind of stresses that the particular structure will see. So if the structure is probably in a configuration where it will experience a higher stress in one direction, the structure has to be strengthened in that particular direction. If there are negligible forces, or if if the forces acting in the other direction are negligible or relatively small compared to the former direction, then we can definitely go for orthotropic material as in this case. So I hope this particular example sums up the relevance of orthotropic materials in engineering design. Having seen the requirement of orthotropic materials, or in general materials with different properties in different directions, let's see the formal definition of an orthotropic material. So in general, a material with two perpendicular planes of symmetry is said to be an orthotropic material. If a particular material have two planes of symmetry, then it is implied that it will have a third plane of symmetry as well, which will be mutually perpendicular to the first two axes. So in a brief, we can say that for an orthotropic material there will be three planes of symmetry. Or to put it in other words, or put it in simple words, you take a material, you rotate the particular material about an axis by 180 degree, and you end up with the same configuration as that of the initial one, then it is symmetric to the axis about which you rotated. Similarly, if you can do the similar exercise about two other axes which are mutually perpendicular to the initial axis, then the particular material we are talking about is an orthotropic material. To show you a few examples, let me start off with a very natural example or a classic example for an orthotropic material. It is wood. So wood has got three directions, one along the axial direction that I am marking here. This is the axial direction. Then we have a radial direction and a tangential direction. So wood has got three different properties in three different directions. Another example which is very widely used in engineering structures is that of a honeycomb. So actually you can take a piece of honeycomb if you can get hold of something at some point of time, and you can actually do that exercise which I described earlier, that rotating about three mutually perpendicular axes, and you can yourself appreciate the fact that this particular honeycomb is an orthotropic material. Obviously, from the figure itself, it is clear that the in-plane properties will be different from that of the out-plane because of the construction itself, but you may tend to believe that the in-plane properties, let's say this is the x direction, let's say this is the x direction, this is the y direction, and this is the z direction. You may tend to believe, or you may tend to think that the in-plane properties are same, but they are different. I have another figure here. So how a honeycomb is constructed, it is something like this. So you have a definite direction called ribbon direction, so where all two ribbons are joined together. So this is the ribbon direction. So usually honeycombs will have more strength along the ribbon direction compared to that of the transverse direction. So EX will be different, EY will be different, and out of plane compression will be also different. So this is another example of an orthotropic material where you have three different properties along three different directions. Another example is human bonds. There is a lot of research going on modeling human bonds with regards to prosthetics, and also it's a very involved area. So believe that the researchers are modeling human bonds as orthotropic materials. Another classic example for an orthotropic material is that of a unidirectional lamina. Actually, this is a very special case of an orthotropic material, but for the time being, you can think this as an orthotropic material. You can see the properties will be different in the fiber direction, and the properties will be much better along the fiber direction, and they will be not that good in the direction transverse to the fiber. They may be slightly weak. Actually, you can call this as a transversely isotropic also, but I'm not getting into that. So I hope we have seen some examples of orthotropic materials. They are very widely used. There's composite laminates are used in launch vehicle structures, satellite structures, aircrafts, and whatnot. Moreover, human bonds are modeled using orthotropic models. So needless to say that orthotropic materials plays a crucial role. Now you have three different properties in three different directions. Now how I can predict the deformation of this particular material once it is loaded? So for that we need to have a sound grip on the engineering constants that are required to define this particular material. So we will have a look at those things in the next video, how the stress strain matrix and everything will be related. Before I wind up this particular video, I thought it will be just nice to add one little thing to the discussion. So you require 9 constants to completely describe or to the stress to strain relationship for a orthotropic material. So this is the matrix. This may look gibberish or this may look a bit difficult to people who haven't seen it before. In the next video I will be explaining it in detail. So to put it in a nutshell, I would say there are 9 constants. As you can see, 6 of them here and 3 of them here. So altogether you require 9 constants to relate your stress to strains, or in other words, if you want to predict the deformation of this particular material against a given loading, you need these 9 constants. You work on commercial finite element softwares, you need to plug in these 9 constants to correctly see how your orthotropic material is deforming. So it is necessary to understand what each of these constants physically mean. We will have a look into those things in the next video. Thanks for watching.